I think my slide is visible from your side. Yes. Okay, so in control designing that I have discussed in my last class. Okay, so that controller designing portion. So which are the most important parts that I have already told you that effect of the negative feedback. Okay, so you all of you know about it. What is the difference between negative feedback and the positive feedback? So you know that most of the class cases. So we have to maintaining the stability. So there is a good effects on stabilities. Okay, so that's why we should much more bother about that negative feedback. Okay, so feedback reduce. So why negative feedback? There is some feature that feedback reduces the transfer function from the disturbances. Okay, so it can reduce the disturbances. Feedback calls the transfer functions from reference input to the output insensitive to the variations in the gains in the forward path of the loop. So two things you can understand. That first one is your disturbance rejection. Okay, so if any of the disturbance is there, it should be overcome by the negative feedback. Okay, so basically negative means it is subtract. Okay, with the that actual response is subtracted, actual value of the response is subtracted with your reference value. Okay, so if you're going to subtract them, then what happened? Then some error will be developed. Okay, so that error will be developed, that will be better. So normally negative feedback means that the amount of error value is less. In positive feedback, then you are adding both of them now. So what happened that you will get that in negative feedback you will get the subtract value, in positive feedback you will get summative value. Okay, that's why that control design may be different. So okay, so that's why you should much more focused about the negative feedback. Okay, so first one is that disturbance. If you give any of the disturbance to your input and output, so the disturbance will be mitigated. Okay, and it will maintain the regulation. Second thing is that is called here reference tracking. Okay, that reference tracking is quite better negative feedback. Positive for the feedback, but positive. Okay, so you are not able to directly. You are not able to directly the effects on stability. Okay, so that's why we are giving much more focused on negative feedback. Okay, then stability. Okay, so stability check means you have to check that stabilities in your frequency domain, time domain. Okay, so a lot of methods are there like your root locus method. Okay, then in phase margin you can write on that Bode plot, Nyquist plot. Okay, means polar dash. Okay, so polar diagrams. Okay, different methods are there. Okay, so we have to test it. The stability normally we are making checking by the phase margin test. Okay, the relation between the phase margin and the closed loop damping factor. Okay, the transient response versus damping factor, that all are related to the stability studies. Okay, that I'll discuss in my later slide. Okay, so it's only that outline of that control design topics. Okay, then regulator design means you can say like that controller designing. Okay, so which are the normal used controller for the power electronics converter, in specialty switch mode power converter, lead type compensator. You know that lead type compensator. Okay, then lag type compensator. Okay, so lead type compensator means PD, you know, the differential compensator, plus you can add some zero. Okay, so so lead type compensator, you can understand that lead means PD type compensator, then lag type means PI type compensator. Okay, then combined, okay, that is PID is there, otherwise other combinations also been possible like lead lag compensator or lag lead compensator. Okay, like other controller also be available like type 2 controller. Okay, type 2 is an example of a PI controller. Okay, sorry, type 1 is an example of a PI controller. Then type 2 controller means it's an PI plus lead controller. Okay, then type 3 controller also be there. It is called PI plus lead controller. Okay, so finally the design example. So you know that portion. So regulator design, another important features for the controls designing of your switching converters. Okay, these all are the most important points. Then that portion I discussed in my last class, that introductory part was there. Okay, so pulse width modulation, how it will work. So that I have been discussed. So input side, you are giving the disturbances like input voltage, load current, and you can control inputs also be there. That is duty disturbance that it is or it is working different. Okay, so all the time you have just check that it is coming as per your requirement. Okay, that is most important thing. Okay, so it is your on time duty ratio and TS means switching time period. Okay, so these all are there. Okay, so that pulse width there. Okay, so you know that how you getting that control voltage, that I have already did discussed in different times. Okay, so that's why I'm not going to repeat it. Okay, then DC regulation operation, that I'm telling you that parametric uncertainty. Okay, in my last class I told you na. So you can see that your functions, your output voltage is a function of your input voltage, load current and duty ratio. Okay, so input voltage is there. Okay, then load current and duty ratios are there. So differences, you are providing the disturbances to your input side, sometimes to your output side. Means input regulation means input voltage regulations. Okay, and your output voltage regulations. Okay, regulation you are going to be checked. Sometimes you are also putting the disturbances to your duty, means input of that compensator. Okay, so very little amount of disturbance you can provide there. Means after differential amplifier, that means your differential amplifier is there, that means your voltage mode control, means output voltage you are sensed. Okay, then the reference voltage is there. Okay, so say some subtraction of your reference voltage and your output voltage. After that, that error signal is fed to the compensator. So you can provide also some disturbance to the addition with your error signal to check that your controller is working fine or not. Okay, so that is called disturbance rejection method. Okay, so that portion I have discussed, that means input variations. Okay, how do you give that input variations, then objective of this regulations. Okay, and in load current variation you can change that load impedance or load resistance up to 50% to 100% to check the stability of your system. Typical output voltage regulation specification is 5 volt plus minus 0.1 volt. Circuit elements at the construction are some specified tolerance. Okay, so tolerance must be there. Then we can go for the DC regulator applications. Okay, regulator applications means you can see the stability, that how much voltage level is there with the presence of some disturbance. Is it coming accurate value? How much error you can going to be compensated? So that study normally did in the regulations application. So what we can observe from this study, so we cannot expect that set duty cycle. So what you mean by the set duty cycle? So if any variation is there in your input side and your output side. Okay, so definitely all the cases, all the times you can observe that your duty cycle will be varied. Okay, am I right? So for maintaining the stability, that I told in my some other classes, that how the duty cycle is changing. Okay, so that I discussed na. So here you can see some regulations portion I have discussed. Okay, that is my previous slide. Okay, so previous module. Okay, that response is not with me. So that you are changing that control signal. Okay, if the changes with the value. Okay, if the changes with that value of your control signal, so PWM width is changing. So how the value of control signal is changing? So if suddenly your output voltage goes high, okay, so it goes high means what happens? So your error will be less. Okay, error will be less. So your control signal will be less. If your control signal is less, so duty ratio will be less, means on time switch on time period also been less. Okay, so your converter working in but very few moments, so switch up condition will be high. Okay, so again it will balance that voltage. So it is not possible only for the set duty cycle. Okay, only for a single set value. Okay, it is not possible. That's why we can go for the variable. duty cycle ratio. Okay, so that's the basic benefits. Okay, why we are going for the closed loop operations of our switching converters. Okay, so basic concept is that duty cycle is varying with the presence of your disturbance, means your system is regulated, your output is regulated. Okay, so obtain for the given constant output voltage. So your motivation is to get that constant output voltage. That's why you are varying the duty cycle. Okay, you are not varying; it is automatically varying. So you said just the logic. Okay, the negative feedback. Okay, so next one is your negative feedback. The build a circuit, okay, that automatically adjusts the duty cycle as necessary. Okay, to obtain the specific output voltage with the high accuracy, regardless, okay, regardless of disturbances or the component tolerances. So I think you are able to understand the basic features of your negative feedback. Okay, so why you are going for the negative feedback? I think you are able to understand that point. Next, you can see in that diagram of your negative feedback. Okay, so negative feedback of a switch mode power converter. So you can say in a single word, switching regulator. Why it is regulator? Because your output voltage is regulating. Okay, with the presence of the disturbances. You can take any of the examples. So here you are, the structure is like a buck converter. Okay, basic DC buck converter. Okay, input voltage is there. Okay, so your sensor gain is there. Here output side sensor gain is there, HS. Okay, so your load current is there, and it is your load. Okay, it is your load. Now what is that sensor? The purpose of the sensor is two things. Okay, first you can sense that voltage. Okay, so sense that voltage directly from your output side. So that is first purpose. Second purpose is that you can provide the isolations. Okay, so what kinds of isolations? That circuit, okay, that sensor to driver, okay, that PWM up to PWM, sensor terminal to up to PWM. So in power electronics converter, normally two type of circuits are there. Okay, one is called power circuit, another is called control circuit. So what is the purpose of this sensor? You can say like that, it is a voltage transducer. Okay, Hall effect voltage transducer. So transducer, you know that sensor is the superset and transducer is a subset. Means all the transducers are sensor. Okay, but all the sensor is not transducer. Okay, so what is the difference between sensor and transducer? Is that sensor normally convert, okay, any of the physical parameter to any of the measurable parameter. Okay, and transducer only can convert any of the physical parameters, okay, physical values to electrical. Only electrical output is there. Okay, so in sensor maybe mechanical sensor, electrical sensor, like that, but in transducer only the example of a electrical sensor. Basically the output of the transducer, okay, is electrical quantity. So you can, it may be in the form of voltage, maybe current, like that. So here you are using sensor, okay, it's called LEM, LV25P of a voltage sensor. Another current sensor also be there, LEMX sensor is there. Okay, but here you can see from the circuit, so you are sensing the output voltage. Okay, it having some gain. Basically that scaling down voltage you will get. Okay, so actual output voltage, okay, it will be sensed by your transducer and you will get some other voltage. So as per the gain of the sensor, okay, maybe it is 12 volt, you are getting 2 volt. Okay, so if you set, you can set the gain of that transducer or the sensor. Okay, it is in your hand. Okay, so such configuration you have to be designed over there. Okay, so if you get that value, then you can compare with that value, means your sense value with your reference value. Okay, it is your reference input. Okay, so your error will be developed here. So what is the purpose of this sensor? So it is isolating. Okay, it means your power circuit is isolated with your control circuit. So any of the faults has occurred in your power circuit of a power electronics converter, okay, so that don't have direct effect on your control circuit. So here one isolation is there, means you can isolate the ground of your power circuit and the control circuit. Another isolation is there when you are feeding your driver, okay, at the end of your driver that fed to your switches. Okay, that time one isolation is there. So your control circuit is protected with the two segments. So one isolation is your output side, another isolation is your driving circuit side. Okay, two isolation is there. So anyhow that fault should not be go there. Okay, so ground isolation is mandatory. Okay, so for the costly device, but you are doing any small circuit for your own testing purpose, for laboratory testing purpose. Okay, in that case you are not using that isolation. Basically that sensor cost is too high. That sensor gain, I am telling you that LEM sensor, LEM25V, LV25V, so it costs near about 3000 to 6000 rupees. Okay, so you can use only for the sophisticated application, like you are using the control board that cost maybe more than lakh. Okay, more than lakh. So in that case you have to use that type of isolation. Otherwise is your any faults is there in your power circuit, that fault current will flow your control circuit, that can damage your costly controller. Okay, so that's why you have to provide some isolation. Okay, that's the basic motivations for using the transducers, okay, in your output side. So here you can compare, then you will get the error signal, then the circuit is common, like you are using that compensator circuit, you will get the control voltage. Okay, after that the PWM modulator is there. That PWM modulator circuit I have discussed in my last module. Okay, you can go to my previous lecture. Okay, previous lecture, so you can understand. Then you will get the delta value, then transistor gate driver. Okay, so in transistor gate driver again we are using opto isolator. Okay, here you are using magnetic isolator. Okay, so Hall effect sensors means magnetically it is isolated. Here we are using opto isolator. Opto isolator means optical isolations. Okay, with your driver and your switch. Okay, so but PWM will be there. Okay, there will be no problem. So MCT2E normally we are using. So when that light will be emitted, optical isolator means take an example MCT2E. Okay, so if the PWM is there, so light will be emitted. Okay, so as per the photosensitive, it is a photosensitive device. Okay, so say 6 like photosensitive device. So if you provide that light, okay, so due to the LED light emission, so that portion will be triggered. Okay, so one LED lamp is there, one transistor is there. Okay, so base point. Okay, the base point of the transistor is normally enabled with that LED diode. Okay, so sorry, the light of the LED. Okay, so that is optical isolation is there, and it will fade to the switching converter. So why it is called negative feedback? So you can see your actual response. Okay, that is your actual response, that HV. Okay, it is coming to the negative terminal of your differential amplifier. That's why it is called negative feedback. And your reference value, that means V reference, is coming to the positive point. So all the point you can see it's an italic. Okay, italic in lower case. So you can say like that, it is look like a instantaneous value. So but it is not actual instantaneous. DC circuit. That's why you are using such kinds of notations. Okay, I think till now all of you are able to understand. If you have any confusion, you can ask me. Okay, so you know the basic structure of the boost converters, buck converter. So I am not going to discuss that operation. Okay, so I think all of you are able to understand the feedback, negative feedback of a switching regulator system. Now that same thing, same diagram, we are using that block diagramic in nature. Okay, so negative feedback. So switching converter, it's used like a blocks. Okay, so when you are compute your switching converter, and before practical study, first you need to do that computational study. Okay, so before that practical study, we can go for the computational study. So at that case, you can see that block I have already been discussed, that input voltage, output current, and your duty cycle. Okay, so it is your control block. So when you are simulating that controller, simulating this converter, means closed loop switching converter in your home. Okay, so you can use that block. Okay, here your circuit will be there. So from where the duty cycle is coming, that output of that block is your output voltage, VT is your output of the block of the switching converter. That VT is function of a input voltage, in output current, load current, and duty ratio, and that output is sensed by a sensor gain. Okay, that sensor is there, Okay, so after passing through the sensor gain, so you will get some scaled, it is called scaled output. Okay, so as per your reference voltage, available reference voltage means which value you are want to be set as a reference value. You are set, you can say like that your output voltage of that converter you want to set as 12 volt. Why 12 volt? Basically that 12 volt, you can say battery charging circuit, the standard voltage is like your 12 volt, okay, like 48 volt, so you can multiplication of 12, okay, or 24 volt, like that. So you are making it a fixed as a V reference is 12 volt, but your output may be different. Okay, so as per the open loop, so output is varying, okay, from certain range. Okay, so yours, what is the purpose of your sensor? So it can convert, okay, so it can convert or it can scale down that value up to the range of 12 volt. If both of the actual voltage, that actual voltage means output of the sensor voltage and your reference voltage, both are in not the same range, so how would you get that error value, means error signal, how would you compare them? That's why both should be in the same range. Okay, and negative values is there. Okay, then compensation circuit is there. After that, control voltage will be developed, and control voltage will be compared with your repeating sequence or the triangular response. Okay, then you will get some PWM. That PWM is coming to the coming as a DT, means duty cycle, and that fed to the converter. Okay, that's the closed loop operations of your switch mode power converter. Okay, simple circuit, and I think all of you are able to understand it. Then effect of the negative feedback. Okay, negative feedback on the network transfer function. So network transfer function means it's a canonical model. Okay, so small signal model, open loop converter. So in your canonical model means you know that AC and DC both are present. Okay, so that perturbations, okay, after perturbating that DC response and AC response both are present. Okay, so that canonical form. So find out that expression was so G gain, if you want to find out that GVD, so if you want to find out that GVD, so make these 2 points will be 0, so VG will be 0 and I load will be 0, so that input voltage is 0 and output current is 0, and you will get that output to control to output duty ratio. Okay, output to control, control to output duty, output transfer function, we will get that one. Okay, same thing VG. Okay, so you are getting that input to output transfer function when your duty is 0 and load current is 0. Okay, and it is your Z output means what? Z output when it will be appeared when VG and DS both are 0. So that DS is 0 and VG, that rate of change of VG, both are 0. Okay, so if both are 0 means both are 0 means what happened? You will get if both are 0 means you can say like that. It is input output current to output voltage. Okay, transfer function is there. Why it is plus minus? It may be plus or minus as per your output voltage developed. Okay, that's why it is written plus minus. Okay, simple thing, you know, I think all of you are aware about that structure. That structure I discussed in the canonical form, and the total entire derivation I was discussed over there in my previous lecture. Okay, so I think you are able to understand. So from where I am getting that value, okay, directly I am using that value. Okay. Then voltage regulation system, the small signal model. So same thing, now you are now it is your structure. So previously you can see the structure, output current. Okay, that output current now you have sensed over here, and it is your sensor gain. Okay, after getting the sensor gain, so it is multiplication, so it is VT. Okay, output voltage is there, VT. So after sensor voltage, how much value will be there? HS into V cap S. Okay, HS is the sensor gain. So output by input. Sorry, it is your sensor gain. Na? So what is your gain? So that output into sensor gain is equal to output means arrow that value HSVS, and it is your Vref cap S. Okay, it is your reference input. I think all of you are able to understand. Now what is the value of V cap E, error signal value? So Vref cap minus HS V cap S. So if you subtract them, so you will get that V, okay, cap So now use the small signal converter model. Okay, we are using small signal converter model. So that model is there. Okay, so from your canonical form, okay, all the parameters are there. It is your output voltage, capped output voltage. Okay, so AC portions, AC component you are only considered here. Okay, you are not using DC component. So perturb and linearize the reminder of the feedback loop. Okay, so now we are using perturbations in the feedback loop. So what is your V reference? V reference equal to capital V ref plus V cap ref. Okay, that's a common thing. And what is your error signal, voltage error signal? E equal to capital V. So it is a signal. So output here, and you are comparing your plus minus means differential amplifier is there, you will get that error signal. So it is GC is your compensator. So then you will get control signal, and your pulse width modulations are there. Okay, so 1 by means you are scaling down, again that scaling down value, and you will get the DES. Okay, it is your cap value. Okay, so all the parameters is look like your small signal modeling parameters, means AC component value. Okay, the regulator system. Okay, small signal block diagram is there. Okay, in regulator system. So here you can see that voltage reference. Okay, like your previous diagram. Okay, so your gain is there, output voltage is there. Okay, so converter power stage, means power circuit is there. Your converter power stage is coming from here. Okay, that transfer function value. Okay, the transfer function values are there. Okay, so converter is, you know, that we output voltage, okay, equal to GVGS D cap S plus GVGS V cap GS plus minus Z out S I load S. So that total form is there. Okay, so you can find out the three transfer functions. Okay, that is combinations. Okay, that total thing is that combinations of your converter power stage. Okay, so VG you can say like that, AC line variations. Okay, so it is the gain of your input voltage, and it is your gain of your duty ratio, and it is the output voltage ZS, Z output S. It is your output load. Okay, the load current variations is there, and you will getting that output variations. Okay, so plus minus all the values are there. Okay, so rest of the thing is same, that your sensor gain is there and your compensation gain GC, and you will get that output of the compensator, and it is your compensator, then pulse width modulator, finally you will get the duty cycle variations. Okay, that duty cycle is there, and that duty cycle is fed to here. Okay, so duty cycle is there na. GVD means VS by DS. Okay, so like that, directly duty cycle is there. That output is what? Output is DS. Point is into G. Here I load into Z out into S. So you can add and minus. It is there VGS. Simple thing. Okay, it is very simple thing. So I think all of you are able to realize that one. Okay, so if you have faced any difficulties, you can ask me again. I can repeat. Okay. Then we have that equations. Okay, that multi-input. Okay, sorry, when put the block diagram, solve that Vs. Okay, so you have that expression. So now you can replace all those values. So from where you are replacing, you know that expression ds, d cap s is there. Okay, so you can replace that value. Sorry, you can replace all those value. Okay, so in the feedback loop formulas are there, you are replacing that value, and finally you will get that expressions. Okay, which in the form of you can say like that, Vref is there 1 by h into t by t plus or t by 1 plus t. Okay. V cap G, it is there GVG plus 1 plus t, plus minus I load G out Z out by 1 plus t, with TS equal to what? HS GCS GVS whole divided by VM. So it is your loop gain. So if you ask anybody, so what is your loop gain, you can ask, you can derive from that expressions from this form. Your loop gain TS equal to product of the gain around the negative feedback loop. Okay, so your negative feedback loops are there. Then feedback reduce the transfer function from the disturbances of the output. So you will get that one. Okay, so previously I have discussed that value in my 3-4 slides back. So again they have written that one. So now they have replaced that value, and finally they can find out that So they can find out that expression, that GVG whole divided by 1 plus TS. So replacing those value and comparing them. Okay, they are comparing, actually comparing that value, and finally they can find out that value. Okay, so with the addition of the negative feedback, the line to output transfer function will be become like that. Okay, then feedback reduced to line to output transfer function by a factor of, okay, so that factors is there, it is 1 by 1, that's why it is like that, reduce. Okay, means that 1 by values are the multiplying with your actual GS, so that's why you can say like the reduce. And TS is a large magnitude, TS is that magnitude is large, the time scale will be large, that's why it is large magnitude, and line output becomes that reciprocal any of the value, so that value will be less. Okay, then it is your feedback reduce the transfer function from the disturbance of the output. Now you can go for the closed loop output impedance. Okay, so original or the open loop output impedance is there. Okay, so Z out is equal to plus minus Vs by I load S. Okay, so that is your duty and Vg. Okay, with the addition of the negative feedback, okay, the output impedance become like that. So you can replace those value, it is coming Z out by 1 plus Ts. Okay, so feedback reduce the output by a factor of 1 by 1 plus Ts. Again, you can say like the Ts is the large magnitude, that's why it is less. Okay, your output impedance generally reduce the magnitude. Okay, so you can say like that your line to output it is less, the value of line to output less, then your output impedance factor also been less, that value also been less. Okay, now you can say that feedback cause of the transfer function from the reference input of the output will be insensitive variation of the gain of the forward path loop. Okay, why? That closed loop transfer function V cap ref to V res. Okay, so it is output by reference value. Okay, so it is coming that 1 by Hs into Ts by that value. Okay, so Ts also it is high, that value also high, so it is more or less same, means 1. So it totally depends upon your sensor gain. Okay, Hs means your sensor gain. Okay, if the loop gain is large in magnitude, that you know that loop gain is large in magnitude, we see basically that multiplications. Now, what was your loop gain? Loop gain is the multiplication of Hs, GCs, GVs. These two are less. Okay, these two are less, but loop gain, that value is large. Okay, so Vm is 1 by Vm is there, multiplication is there. Okay, so that Ts value is very high, means definitely loop gain is high. Okay, Ts value is high means loop gain is high, that's why it is written that loop gain is large in magnitude, that means mod T very greater than 1. Then 1 plus T, what happened? It is similar to T, okay, more or less, and your T by 1 plus T equals to 1. That's why it is written that T by T equals to 1. The transfer function becomes, it is 1, it is coming 1 by Hs. So how it is coming 1 by Hs? Means V cap S by V cap S. So you can understand, which is independent of the gain of the forward path loop. Okay, these results apply equally well to DC value. So you know that it is sensor gain. Sensor gain is more or less DC value. So gain means almost DC. So 80. So definitely it is almost coming a DC value. Some gain value is coming. So V by capital V ref equal to 1 by Hs 80 equal to T0 by 1 by. So both are more or less same. It's 1. Okay, so it is coming 1 by 80. Okay, so you have to construct that important quantities, okay, in the Bode form. Okay, so Bode diagram you can go. So first modulation, so 0 dB means it is coming some of the constant value, then that value decide your Q value. Okay, then you can see from the diagram, from that, sorry, from the transfer function you can write that one. So second order poles are there. Okay, first you can say like this, second order pole, so that pole is greater than that pole, that two pole frequency is less than the zero frequency. Okay, that zero frequency, then another pole is there, omega p2, that frequency is greater than of your zero frequency. So p1, okay, p1 frequency less than with your omega z frequency. Okay, and omega z frequency is less than to your omega p2 frequency. So first you can see that these two poles are arrived first, so that's why the minus 20 dB say like that minus 20 dB per decay into 2, so minus 40 dB per decay. So you can say like that AP1, so first pole 1 is coming, then 0 frequency is coming, and finally another pole frequency is coming. So it is your cutoff frequency. So when 0 dB line is cut, okay, so that is your gain. Okay, now it is your gain plot. So gain cutting with your 0 dB line, so that will be your crossover frequency. It is your first crossover frequency. So you can say like that white is minus 20 dB per decade, second order system. Okay, then up to it is coming FZ. Okay, up to FZ. Then what happened FZ? It is added with plus 20 dB per decade. So that's why minus 40 dB per decade plus 20 dB per decade. So it is coming minus 20 dB per decade. Okay, from FZ to FC, sorry, FP2. Okay, after that again some pole is there. Okay, so then minus 20 dB per decade plus of minus 20 dB per decade, so it is coming minus 40 dB per decade. Okay, so then it's coming like that. So the crossover frequency FC mod t equal to 1. Okay, so 0 dB line means it is 1, logarithm dB means logarithm 1 means ln1 means is 0. That's why you can say like that crossover frequency, it is there, it is 1. Okay. So now you are going to be approximated that value 1 by 1 plus t and t by 1 plus t. 1 by 1 plus t, it's a very large value. Okay, so t by 1 plus t means when it will be 1. Okay, when t is very greater than 1. For t is very greater than 1, it is coming 1. So 1 by d by t, it is 1. So when t is very less than 1, okay, t is very less than 1, so it is coming only t. Okay, basically that portion will be less compared to 1, so it is t by 1, so it is coming only t. Then the same thing, okay, 1 by 1 plus ts. Okay, so when t is mod t is very greater than 1, okay, so that is very greater than 1 means 1 by ts, directly it will coming. And when t is very less than 1, so it is coming 1. Okay, for t is mod t is less than very less than 1. Okay, now we can draw that Bode diagram. Okay, for example, for the construction of t by 1 plus t. Okay, so it will be 1 first condition, it is 1 minus means that 0 dB line. Okay, that one 0 dB line. Na? So first condition mod of t by 1 plus t. So and t is started from that value. Okay, then the same thing also followed like your previous equation. So what was your transfer function? That was your transfer function. Okay, so it is starting from sum of the value, gain value, then it is maintaining that value. Okay, so there is no peaky in nature. Okay, there is no q. Okay, so directly it is coming fp1 to fc up to fz. Okay, that is mod t value, that one, second one. Okay, then up to fpz, so it is crossover frequency, basically 0 dB line cutting portion, then it is minus 40 per decade, the same thing. Okay, now example for the analytical expressions. Okay, analytical expressions for the approximate reference to the output of the transfer function. Okay, at frequency sufficiently less than that the crossover frequency, the loop gain ts large in magnitude. Okay, loop gain ts is large in magnitude, the transfer function from the reference to the output becomes, okay, v cap s by v cap reference, okay, equal to that 1 by hs into ts by that portion I have discussed. Okay, 1 by hs value. Okay, so now you can replace all those value. Okay, so if the desired behavior from this is a desired behavior, the output follow. Okay, the output follow the reference according to the ideal gain. Okay, ideal gain is 1 by hs. The feedback loop works well the frequency where the loop gain ts has been the large magnitude, so you have to multiply that value. Okay, so the frequency at the frequency above the crossover frequency means mod t less than 1, the quantity t by 1 plus t then has the approximately equal to 1, and we obtain v cap s whole divided by v cap reference equal to 1 by hs into ts by 1 plus ts. Okay, so it will more or less that ts value will be that value is less than 1 means you can compare, you can negligible that one. So finally it is coming that ts by HS. Okay, it is not very less than, but it is less than 1. So you can means omit that value. Okay, it is coming only 1, so it is coming TS by HS. So you can replace that value of TS. The value of TS equal to what? HS GCS GVDS whole divided by VM. Okay, so that is HS meter cancel. So is that value. Okay, then finally you will get that one. This coincide with the open loop transfer function from the reference to the output. Okay, it is reference to the output at the frequency where mod t less than 1. The loop has essentially no effect on the transfer function from the reference to the output. Okay, so there is no effects on that sensor gain. Okay. So what is terminology? The open loop versus closed loop. Okay, that you can observe over here. So original transfer function before introducing the feedback, that is called that open loop transfer function. That GVD, okay, S G VGS Z out S. So that is your open loop when there is no feedback path. Okay, and upon the introductions of the feedback, this transfer function become the closed loop transfer function. Okay, when it will be made to the closed loop, 1 by HS into TS by 1 plus TS. Okay, G of VGS by 1 by 1 plus TS, then Z out. So that is your closed loop one. So your loop gain is TS. Okay, that is your loop gain. I have discussed here previously. The TS your loop gain. So now we can go for the stability. So what is the motivation of the stability that I discussed? So any of the in any case of sorry, is any case of means disturbance, okay, your output should be maintained. Okay, means your desired value. Okay, so if it is not maintained to our desired value, so you can say like that it is not stable system. Okay, so if you giving some of the disturbance and your output is deferred from your equilibrium point. Okay, so you can say like that your system is not stable. So there are different methods, okay, in switching converters to checking their stability. Okay, so what kinds of method, you know that I told you na, in Roots-Lucas plot. Okay, so if you have the transfer function of your system, you can directly draw that transient response, means step response, then you can plot it for the Roots-Lucas. Okay, then you can also go for the frequency domain. Okay, so all the cases you can understand that different methods you can implement it, like your basic control system idea. Okay, that you know that formula, but you have to maintain, you have to specify your system in LTI. Okay, so linear time invariant system. Okay, so that some consideration you have to think about it. So what is their opinion? So even though that original open loop system is a stable, okay, and the closed loop system transfer function can be unstable and contain the right plane poles. Okay, so if that point having that means when you are making your system in the feedback loop, means negative feedback loop, so you have to find out the characteristics equations. Okay, if you have that characteristics equation and you are able to plot that, you are able to find out the roots of the characteristics equations, and you can get that roots in your the poles. You are concerned about the denominator, not for the numerator. Definitely there is an effect of numerator. If that one root in your right plane of the denominator, okay, then you can say like that is an example of a non-minimum phase. So it having some other problem that I discussed in my previous slides. Okay, there is no such problem in your magnitude. There is no such direct effect on your magnitude, but the effect in your phase. Okay, so if there is additional phase lagging, so that may cause your system additional delay, that may cause your system additional undershoot, that may cause your system sometimes instability. Okay, that's the problem. Okay, so here in the stability for the closed loop system, no pole should be in your right plane. Okay, so if there is any of the right plane pole, so you can say like that your system is unstable. So what is written over there? Even when the closed loop system, okay, is stable, okay, the transient response can exhibit the undesirable ringing or the overshoot. Okay, so it totally depends upon your parameter decimation. Okay, so your system is stable. Okay, But if you plot in your step response, you can see initial phases lot of transient, means disturb, means oscillations are there. Okay, means huge overshoot, huge undershoot. Okay, then it is maintaining that steady state value after a certain point. So a lot of overshoot is there. Overshoot means you can say like that overshoot the range maybe in to 100%. Okay, means that value of your set value. So it is another values is coming. Mathematically that is right, there will be no problem. Computational way in MATLAB in India, that platform you can check, there will be no problem. But the problem when you are plot those, sorry, that problem has occurred when you are practically implement those parameter value. Okay, so that may cause of what? So if the switch having some voltage stress and due to some dynamics of converter dynamics and the stability issues, that input voltage means that voltage appear across the switch is coming twice of its standard value, then automatically that switch will be burned out. Okay, so at the time of designing you should think about it, and you have to design that optimal values of inductor, optimal values of inductor, and the okay, so that it will be in limited region. Okay, so you should think about all those values, all those parameter, all those considerations. Okay, if you are not able to think about it, so it may cause for damage of your system. Okay, so practically when you are going to design, so you have to overcome with your some practical issues like your ringing effect. Okay, means unwanted oscillations will be there at the time of any of the signal. Okay, then overshoot will be there. Okay, so that is normally observed for of what, due to the high Q factor of the closed loop poles. Okay, and the vicinity of the crossover frequency, that means the selection of the parameter is most important issue. Okay, that may be there for the crossover frequency, means phase margin, you can say like that. Gain is cutting with your 0 dB line, na? So it's related to your gain margin. Okay, so that gain margin, the how much gain margin you can tolerate. Okay, so how much phase crossover frequency is there. Okay, sorry, phase margin is there means gain crossover frequency, means phase gain crossover frequency, your phase margin is related to your gain crossover frequency. So from this diagram you can see that your gain is cutting, na? It is gain is cutting that point, that FC. So what kinds of crossover frequency? It is your gain crossover frequency, but you are getting that phase margin like that. Okay, so you have to think about it. Okay, when you are going to be designed for that. So sometimes what happen, you have some limitations. Okay, some converter having, you are getting, you are able to design the converter for the predefined value. Okay, that values are there, so there is no such changes in your hand. Okay, that input is already specified, application oriented, na? So you cannot design your own converter like your that idea is coming in your mind, you are directly fabricate that one. It's not like that. So you have to design the converter as per your applications. Okay, how much your load required, how much your, what type of input is available, it is AC input available or DC input, how much your load, means AC voltage, AC you are going to be drive for AC load or you are going to be drive for DC load. As per your application, as per your requirement, you are able to design the converter. Okay, so it is, everything is not in your hand, but switching frequency, everything, some of the point is in your hand. So how to control that oscillations, how to control that maintaining the stability, then you have to think about your the suitable compensator. Okay, you have to think about your switching means suitable compensator or the control circuit. Okay, which type of controller you are going to be used for the designing purpose, that you have to decide. Okay, so if you are not able to decide that value, so it will give you that means not the suitable results. Okay, so it will give you some, provide some erroneous results. So that compensation design or the controller design is one of your main objective. Okay, so basically that due to the parameter selection, so all the times is everything is not in your hand, but controller design, it is in your hand. Okay, you can design a suitable controller. Okay, so that's why it is written that feedback destabilize. Okay, that feedback may be destabilized of the system for the denominator, that 1 plus Ts, that is coming in your previous equations. Okay, terms in the closed loop transfer function contain the roots in the right half planes. Okay, that may cause for the roots in the right half plane. That means with the positive real parts. Okay, that is positive real parts. Okay, the TS is a rational functions. Okay, from ns by ds, ns by ds. Okay, where ns and ds are the polynomials. Okay, so rational function is a polynomial. No? When we can write, okay, so ts by 1 plus ts, you can write that ts is ns by ds. So you can simplify it, is coming ns by ns plus ds. Okay, and 1 by ts, you can write only ds by ns plus ds. These two equations, you are thinking about these two equations, no? These two equations you are thinking, so two equation you are getting. So it could evaluate the stability by evaluating ns plus ds, factoring root illuminated. Okay, so you can see that different stability you can use for checking your system dynamics. Okay, the determination of the stability directly form of TS. Okay, so what kinds of methods you are using? Nyquist stability theorem. It's a generalized result, so you can able to use it. A special case of Nyquist stability theorem. Okay, so Nyquist stability theorem, what is that? The phase margin test. Okay, that is testing by your phase margin. So how much range of your phase margin? It is positive or it is negative. If it is positive, so what is that value? If it is negative, how much is value? Is this stable? Example of a stable phase margin or the negative unstable phase margin? From there you can understand. That allows, okay, that points are there, allows the determination of the closed loop stability. That phase margin, actually that phase margin test allows the determination of the closed loop stability, whatever whether that 1 by 1 plus ts contain the RHP poles directly from the magnitude and the phase ts. Okay, the good design tools. Okay, good design tool means which mathematics you are going to be followed. Oh, mathematical tools normally you are using, na, for modeling of your switch. Okay, then modeling of your, then designing of your controller. So all the time you are using mathematical tool. So which one is much more suitable, that you have to check. Here inside how TS should be shaped. Okay, how TS should be shaped to obtain good performance in the transfer function containing 1 by 1 plus TS term. Okay, that you need to find out. Okay. So the phase margin test, from the phase margin test, what you can do, a test of TS. Okay, determine whether 1 by 1 plus TS contain RHP pole. Okay, the crossover frequency FC is defined as the frequency where T into T omega, na? So T into J 2 pi FC equal to 1, 0 dB line. 1 means 0 dB line all the time. And phase margin phi n is determined the phase of TS at FC, means crossover frequency, means gain crossover frequency, how much deviation with your 180 degree line. Okay, that is your phase margin. As follows, phase margin is 180 degree plus angle of T J2 FC. Okay, means at crossover frequency, that angle is there, na? That crossover frequency, that angle you have to find out. Okay, in phase plot. Okay, so how it is differ with your 180 degree, that is your agenda. Okay, to find out the phase margin. If that exactly one crossover frequency and DS contain no RHP pole, then TS by 1 plus TS and 1 by 1 plus TS contain no RHP pole, wherever the phase margin will be positive. Okay, if there is no RHP pole, mean unstable system, your phase margin goes to the negative, means you can say like that, phase margin is negative. If there is no RHP pole, means if your system is stable, so your phase margin phi m is positive, that I am telling you. Okay, that portion. So now you can check it. Okay, now you can check a loop. So it having some stable closed loop system, it is your mod value. Okay, mod value is there. So that equations is the first one. Okay, so that transfer function I telling you now, that example of that first pole frequency, that AP1, two poles are there. Okay, this peaky nature is there due to what? Due to Q value. Okay, that amplitude is your Q. That amplitude is your Q. You have to calculate that value of Q. Okay, and it is an angle. So pole is there, then 0 is there, then FC crossover frequency, the 0 dB line. Okay, 0 dB line means 1. That mod d equal to 1. Okay, that line cut off crossover frequency, and after that what happened, some another, okay, so they have only considered only 1 0. Okay, and they have only one pole and 1 0. Okay, first pole then 0. Okay, they are not considering any other thing. Okay, I think one pole also there. Okay, so here that portions. Okay, it is not mentioned but it is there. Okay, so angle is there first. Up to this portion 0 means there is no changes of their angle. Okay, 0 dB line. After that, due to the pole, two poles are there, it will be goes towards 90, minus 90 into 2 consecutive poles are there for the single frequency, so it is coming up to minus 90. Okay, that portions. Okay, up to coming minus 90. Then 1 0 is there. Okay, so 0 is there, so it goes up to minus 180 plus 90, so it is reducing that value. Okay, that phase margin, so sorry, that phase angle, so coming to the 90 up to which point, this point. Okay, this point means your another pole is there. Okay, after that points what happened, so another minus 90. Okay, so what happened, it is fixed up to minus 90. Okay, so coming to 1 minus 180 to minus 90. So that point it is minus 90. So what is your phase angle that you have to find out? So FC it is cutover frequency, gain crossover frequency to 0 dB line. So you can increase that points here. So you can able to find out that value. Okay, that minus 180 to how much values is there? That value is there. So it is coming minus 112. So phase margin equal to is 60 degree. Okay, 68 degree means it is stable. Example of a stable. Then you can go for that.
Hello, sir.
Another example. Okay, you are go for the another example. Okay, that loop gain leading unstable. Okay, previous one was stable. It is unstable. It was unstable. Okay, so it is an unstable closed system. Tell me.
Hello.
Yes,
Sir,
yes.
what
Tell
is
me.
the practical meaning? What is the practical meaning of this phase margin in the converter, sir? I mean, in this.
Practical, I'm telling, I am coming. Okay, it's a good question. I'm coming. What do you mean by practical meaning of phase margin? I'm coming. Okay, I'm coming.
Okay.
Okay, after complete my session, you will get your answer. If you are not getting that answer, so then again I am coming. So actually, what happened? Actually, that subjects I am giving here some of the mathematics, some of the theoretical analysis, theoretical aspects. So if you have some experimental result with you, so we can define it, but some response is there in my next slide, so you can understand. So there is some direct relation, I'm telling you, there is some direct relation of phase margin with your damping factor. Okay, that zeta value. Are you getting my point? So zeta value is there now, so damping factor is there. So if you in your previous example, you can see that phase margin is coming in the range of 68 degree, means nearer to the 70. Okay, so your damping factor, if you go for that, in my experience, I am telling you, so there is no hard and fast rule. Your damping factor nearer it is coming 0.68. Okay, it is from my experience I am telling you. Okay, nearer to the 0.68. So 0.68 means it is not the critically damped. It is under damped system, but it having less magnitude, and you can see that direct effect of your Q factor. Okay, that due to the low Q factor, you can see that high Q factor means it is peaky in nature. For low Q factor, it is the peak is quite less. If the peak is less, then you can see there is some overshooting change in your physical system. Okay, overshooting change means when you are checking your reference tracking of the converter, when you are checking your reference tracking of the converter, you can observe there is that response it having less overshoot. Are you getting my point? Reference tracking, that your reference Vref is there, you are adding some of the disturbance. Okay, step disturbance to your reference, means you are adding some reference additional step voltage with your V reference voltage. So you will get some your as if your converter is working properly regulated and it is working in the state. So when your out overshoot. Okay, but it is perfectly tracking. If your system is nearer to the critically damped, okay, so there will be no overshoot. automatically it will fix. So that is your physical realization of your phase margin to your damping factor to your quality factor to your real response. Okay, so I am coming another slide so you can understand. Okay, so that's the physical realizations. Okay, from the phase margin with our practical system. Okay, they are related to your damping factor. Okay, are you getting my point?
Yes, sir. Yes, sir.
Okay, and there is some time domain waveform, so you can understand better. Okay, so previous example it is for the stable system. So now you can see it is example for a unstable closed loop system. Okay, example. So it is your mod value. Okay, modulus that is Bode means your amplitude and your angle. Okay, two are there. So that key that peaky nature. So two poles are there. Okay, so first one pole, then another pole. Okay, so first one pole means it is how much you can say like that minus 180. It is coming up to minus 180 means there are two consecutive pole for that frequency. Okay, so due to two pole it is coming minus 180 degree. Again another pole is there. Okay, that pole means it is coming another 90 degree. So it is coming up to 270 degree. Okay, up to 270 degree. Okay. So here you can see your phase margin. Okay, so it is your then it is cutting your means 0 dB line. Okay, so 0 dB line sorry, it is cutting. So you are able to find out that crossover frequency over there and you are able to find out that phase margin. So here you can see your phase margin is coming negative. Okay, so 180 degree minus of 230 degree. Okay, so it is coming phase margin is negative. So you can say like that your system is responsible for, it is example of a unstable system as your phase margin is coming negative. So the relations of the relation between the phase margin, that question has come, that phase margin and the closed loop damping factor. Okay, so that relation we have to think about it. How much phase margin is required? Okay, that is a common question. Okay, so a small positive phase margin lead to the stable concept, stable closed loop system. Okay, so small positive phase margin. Are you getting my points? Having complex pole near the crossover frequency with high Q. Okay, that transient response exhibit the overshoot and the ringing. So normally what happen when that ringing effect and overshoot is coming due to the complex pole. Okay, due to the complex pole nearer to your crossover frequency. Increasing the phase margin reduce the value of Q. Okay, so if you increase the value of phase margin, so your Q value is reduced, means peaky nature will be reduced. Okay, obtaining the real pole with no overshoot is and ringing. So you have to keep in your mind that phase margin you have to be in moderate zone to reducing the value of ringing and that overshoot. Okay, that I am telling you that rise time will be less. Okay, phase margin is less means rise time will be less. Okay, rise time is less means you will get some oscillations, initial oscillation means transient oscillations. Okay, that requires for a large phase margin, and high Q means it will be peaky, so it should be less, your Q should value will be less. Okay, the relation between the phase margin and closed loop Q is quantified in these sections. Okay, so you can see the diagram so you can understand. The simple second order system is there. Okay, so single second order system, so it is minus 20 dB per decay means one pole is there. Okay, then cutoff frequency, then another it is minus 40 means it is another pole is there after crossover frequency. Okay, so that value is like that. Okay, so you can see that phase value. Okay, so minus 90 started. Okay, up to that value, then it is coming up to minus 180 degree at f0. So how much value is there? You have to find that value, phi m. Okay, so consider the case of TS. Okay, Y approximated value vicinity of the crossover frequency, TS equal to 1 by S0 plus into 1 plus S by omega. So it's a gain with some gain and the value. So two poles are there. Okay. So here you can see your TS is given. Okay, so you have to find out the TS by 1 plus TS. So that value is coming. Only two poles are there in the system. Okay, it is coming 1 plus S by Q omega C and S by TUSC. So your omega C is your transfer frequency is like that 2 pi FC, and Q value is coming that root under omega 0 by omega 2. Okay, that is coming from that expression. Okay. So now you can see that low Q approximations. Okay, so low Q case, what will happen? So at that value, so low Q value, so directly that value is coming minus 20 dB. Okay, so your Q value is Q omega 0 by omega 2, and your expression will be Q omega C equal to omega 0, and finally you will get that value Q equal to F0 by Fc. Okay, Q equal to F0 by Fc, that value. Okay, so it is your low Q value. Okay, then high Q value. Okay, in high Q value what happened, you can see one peaky type nature is there. Okay, that peaky type nature. For low Q value there is no peaky type nature, directly it is coming like that way. Okay, your FC, your F0 is there, then F2, F1, F0, F2, all are directly coming. Okay, so but low Q value, so your always motivation should be like that, your Q value should be low. Okay, so it's not very low, it's not very high, it should be moderately low. Okay, in the nearer to the low. Okay, otherwise if it is not low, so you can see that that peaky type nature is there. Okay, that value Q equal to F0 by Fc. Okay, that value, and additional thing you can observe that other both part there will be no changes, but the peaky type changes is there. Okay, it is practical one. Sorry, that is your actual one, and it is your practical one. It is like that way. So it is coming minus some Q value you can observe over here. That Q again it will be same, but it will be in peaky type nature. Okay, so Q versus QM means phi m. So phase margin. Okay, solve the exact crossover frequency, the equivalent. Sorry, evaluate phase margin, express the function of phi m, and result you that Q equal to cos phi m root under whole divided by sin phi m. So they are using some mathematical expressions with the value of Q. Okay, so you can calculate that value, and you can see that Q versus phi m. So your Q value is in dB. Okay, minus 20 dB to up to positive 20 dB. So you can see if you increase that phase margin, so up to 90 degree, you are increasing from 0 to 90 degree. If it is your phase margin, you can see it is Q value is very high, your phase margin is less, nearer to the 0 to 10. Okay, so at 50 to 60, phase margin is 50 to 60, you can see like that your Q value is moderately 0. That I am telling you now from my just couple of slides back, I'm telling you now. So from my experience, I'm telling you that phase margin should be in the form of 60 degree range. Okay, that will giving you some critically damped system. Okay, so here you can see nearer to the critically damped system. So you can see, you can understand that Q value is 0 dB at least, and if phase margin is 52, Q value is 0.5, it is coming minus 6 dB. Okay, so minus 6 dB value, that is your phase margin is 76 degree. Okay, so increasing the phase margin, your Q value is decreasing. So you can understand more or less it is inversely proportional, but exactly not inversely proportional. So some curve is there. Okay, that is not a linear curve, it is a non-linear curve. So you have to find out the linear zone in this curve. Okay, so in this linear zone of operation, okay, you have to select the value of phase margin. Okay, so you can see the linear zone is more or less coming 30 degree to up to 76, maybe like the 75. So from these portions, okay, so from this portion you are getting the linear. Okay, so you have to draw the tangent. Okay, so if you are able to draw the tangent, so you will get that value. Okay, that linear zone you have to select that one. Then we can much more giving our thrust to the transient response, that I am telling you now, transient response versus damping factor. So you can directly see the diagram, then we can talk about the mathematics. Okay, so here you can see that omega c in radian. Okay, so that critically damped, and which one is your critically damped? Here you can see in step response. So first one Q value is 50, so huge oscillation is there. So one is, it is in step response. Okay, so one is your reference, so it is coming nearer to 2, means it is 2 minus 1 whole divided by 1 minus 1 by 1. Sorry, that how much percentage overshoot is there? 2. It is nearer to the 2 value. 2 minus 1, means maximum value minus reference value whole divided your reference value into 100%. So it is 100%. So almost 100% percentage of overshoot is there. So that may cause damage your switches. Okay, that oscillations. Okay, when you are changing your reference value, okay, that reference voltage tracking you are doing, you are observing to check your disturbances. Suddenly you can see that peak is coming, that your reference value is there twice of that reference value, then it is settled down. Okay, that means what? That means that huge value is appear across to your switches. Okay, that may dash not like only switches, maybe inductor, capacitor, all the time those are connected parallel with this one. So directly it having effect to your devices and your components that may damage your system. Okay, that's you should keep in your mind. So Q value very high is not acceptable. So again, huge value of Q means less value of phase margin. So Q should be in moderately low. So more or less at nearer to 1. Okay, so which values are there? You can see that Q value is 0.5 and very good value Q is coming 0.5. Okay, that 0.5 value are more or less critically damped. Okay, so your agenda should be like that, your system having critically damped. Okay, so means it will not like a under damp and over damp. Okay, it is pretty more or less critically damped. Okay, so there will be no overshoot, no undershoot, and no steady state error. Okay, that is your consideration. So more or less Q equal to 0.5, you are getting that critically damped system, and it is omega c t in range. So you can say like that value. So in radian values are there. Okay, 2 pi fc value is given. Okay, so you can find out that only fc. So 5 divided by 2 pi is what? 5 divided by 2 pi means just wait. It is coming 0.79 means 0.8. Okay, so it is coming 0.8. So damping factor nearer to your 0.8 means 0.8 means nearer to your approximately 1. Okay, so it is, you can say like that, it is critically damped. Okay, so you can understand that Q value is less, that reduce that value Q from 50 to 0.01. Very low Q value is your example of a overdamped system. Overdamped system is so sluggish. So in your switching converter application, as per your switching converter, your system should not be so sluggish. So your concept should be like that, system will be very fast. Okay, if your response time is very low, so then what happen? Any disturbance will be there, so it will take a lot of time to overcome the disturbance. So your system will be damaged. Okay, so huge disturbance is there, so that may damage your system. So your target will be like that, you have to moderately set that value. Okay, so moderately set that value, so you can overcome the disturbance without having huge overshoot, without having sluggish response. Okay, so moderately you have to select. Okay, so you should not select very low Q value and you should not be select very high Q value. So moderately Q value you should select nearer to the 1 to 0.5. Okay, in between 1 to 0.5. Okay, so it will give you some little overshoot to some of the critical range. Okay, and it will directly affect having effect to the zeta value. So critically damped value means zeta value will be what? Zeta value will be 1. Okay, and you can see from the diagram. Okay, so you can see that critically means 0.5, it is zeta value is 1. So 0.75 means zeta value is less than 1. You can say like that, 0.75 means zeta value again it is coming nearer to the 0.7, like that. 1 means it is nearer to the 0.5. Okay, like that. I think all of you are able to understand. So if you have any doubt, you can ask me, so we can end today's session. So in my next session tomorrow, I will discuss with some controllers. Okay, so basic controllers are there. Okay, like PI, then lead, lag. Okay, their applications. So till now, if you have any confusion, you can ask me. So if you have any doubt, you can ask me. Okay, so I think you do not have any, most of you do not have any doubts. Okay, so I can stop today's session.